Go over test 2. The first problem was to use your calculator to estimate the value of a log. This would be using the change of base formula, And so what we can do is take the natural log of 23 divided by the natural log of the base, which is 4, and that gives us 2.2618 approximately. The second problem was true or false. This one is false. This is our quotient property of logarithms. The log of a divided by b would equal the log of a subtract the log of b. So this one is false. The second one is true. And this is our product property of logarithms. The log base b of 2 plus the log base b of 3 would equal the log base b of 2 times 3, which is 6. For this property to work, both of these bases do have to be the same. The next one was to rewrite log that into exponential form. To do this, we take the base of the log, swing it over to the other side of the equation. It becomes the base of our exponent. So the log base 3 of 6 equals x can be written as 6 equals 3 to the power of x. Going the reverse direction, this is an exponential form. We want to rewrite it in log form. The base of the exponent will become the base of the log, swinging over to the other side, leaving us with y equals log base 5 of 16. These two problems were to practice using the properties of logarithms. The first one is to expand. We have the log base 3 of a quotient here. So at the log of a quotient, we can separate that into two logs using subtraction. So we get the log base 3 of the numerator, subtract the log base 3 of what was in the denominator. Then we can use our product property and subdivide this logarithm into log base 3 of a plus the log base 3 of b cubed, with the multiplication turning into the sum of two logs. Then we can use our exponent properties. The exponents on the value of b here can become a multiplication. That would be our power property of logarithms. And then the square root of c we can write as c to the exponent of 1/2. A square root is the same thing as the exponent of 1/2. The exponent we can pull out in front also using our power property. And then we've expanded the logarithm as far as we can into the log base 3 of a plus 3 times the log base 3 of b, subtract 1/2 the log base 3 of c. Going the other direction, we've got an expanded logarithm and we want to condense it into a single logarithm. So with the addition of two logs, we can, first let's take care of those multiplications. The multiplications will become our exponents. So we get the natural log of t to the 1/4, and the 3 here times the natural log of t can be rewritten as the natural log of t cubed. Then we can use our multiplication property. If we have the sum of two logs with the same base, these natural logs are both log base e's. We can combine them into a single logarithm using multiplication. And then the subtraction using our quotient property, this would become division, which we can then write as the natural log of 8 t to the 1/4 over t cubed, or the natural log of 8 4th root of t over t cubed. Either format is fine. You could combine the two t's here, but I didn't worry about that when I was grading the test. Going on to the next page, we're solving an exponential problem. I've got a couple different approaches here, and there are actually a couple more. The way I prefer to do these, since I've got an exponent equal to a value, is first rewrite this in logarithmic form. So the base of the exponent 5 I bring over to the other side to become the base of my log. So I've got log base 5 of 8, and then that will equal my exponent 4x plus 2. And then I can solve using the usual arithmetic techniques. I can subtract the 2, divide by the 4, and get the log base 5 of 8, subtract 2 over 4. I can run this through my calculator using the change of base formula to calculate this. And I believe this came out to be about a negative 0.117. Another way to approach the problem is to take the log of both sides. I went with the natural log. The common log would work just fine. So if I natural log both sides of the equation, that allows me to use the power property and pull the 4x plus 2 exponent out in front as a multiplication problem. And I seem to have this in here twice. Sorry about that. And then since this is multiplication, I can get rid of the natural log of 5 by division. leaving the 4x plus 2, and then again subtract the 2, divide the result by 4, and I've got my x solved for. This problem is a log equation. I've got the sum of two logs equal to a constant. Using the property of logarithms, since I have a log plus a log, I can combine them into a single logarithm using multiplication. So I've got the log base 4 of 2x subtract 1 times 5, combined into a single logarithm. And then went ahead and simplified that for 10x subtract 5. Now I've got a single log equal to a constant. I can rewrite that in exponential form, taking the base 4 here, swing it to the other side to become the base of the exponent, and I've got 4 cubed equal to 10x subtract 5. Simplifying the 4 cubed, I get 64, add 5 for 69, divide by 10 for the 6.9. This problem's similar. A couple things that are different. I've got a log subtract a log, and instead of being equal to a nice rational number, my result here is equal to an irrational logarithm, but it is still a numerical value. This will actually make things a little bit easier. So again, using my properties of logarithms, since I'm subtracting two logs with the same base, I can combine them into a single base, base 6, a single log base 6, and use the quotient of 7x over x plus 2 equals a log base 6 of 5. Since I had the log base 6 equal to a log base 6, the one-to-one property of logarithms allows me to rewrite this as simply 7x over x plus 2 equal to 5. You could also think of this if I raise both of these as an exponent, 6 to this power equals 6 to this power. The 6 to the power undoes the log. They cancel each other out, leaving us with this. And then again, once we've gotten to here, not a bad problem to solve. I can multiply both sides by x plus 2, get 7x equals 5 times the x plus 2, distribute, subtract the 5x, divide by 2, and I get my solution x equal 5. I've got a word problem here, pretty standard exponential problem. It is compounded continuously, so that tells me I use the a equals p e to the rt formula. If I was compounding annually or compounding continuously, I would use a different formula. I'm interested in getting $57,000 to double, and I am given the interest rate. So I can put the $57,000 in for my initial deposit, and I can put my interest rate in. I do have to move the decimal 2 places because the percent means I'm dividing by 100. And I want my money to double. So if my original debt investment's $57,000, doubling that would be $114,000. So I want to know how many years will it take for this deposit to grow to $114,000. Solving, I'd first divide by the $57,000, which would leave me with a 2 over here. And then because I've got a base e here on my exponent, I can natural log both sides, or think of it as rewriting an exponential form with a log base e. That's what the ln is, log base e of 2. And that would leave me equal to the exponent over here on the right-hand side. I can divide, run it to my calculator, and I've got t is approximately 27.3 years for my money to double at this interest rate. This one's a growth model. We've got a population of cholera. It starts at 6 million at time t equals 0 hours, growing to 785 million at time t equals 7 hours. So when I did this problem, I simply thought of the population being the number of millions of bacteria and used 6 and 785. If you choose to use 6 million and 785 million, it works out exactly the same way. So I know my initial population is 6. I want to know when I know the population grows to 785 after 7 hours. What I don't know is the growth rate. I need to find k. So I'm going to divide by 6 to get my exponent function over here by itself. Then I can rewrite as a natural log. That allows me to get at the exponent. Divide the result by 7 and run it through my calculator, which gives me a growth rate for k of 0.6963, and then my population model is 6 times e to the 0.6963 times t. Then I can use that to answer the second half of the question, estimate the number of bacteria after 12 hours. Substitute 12 in for t, do the calculations, and here's where I need to remember that this is my population in millions of bacteria. So I've got 25,523 million bacteria, which would be 25.53 billion bacteria are present after 12 hours. To find an inverse function, the way we get these started off is we do have to swap x and y. And I just want to point out here, g of x is x subtract 2 squared, which is a parabola. And so it's been restricted that x is greater or equal to 2. That way I'm only looking at half of a parabola, so it is still a one-to-one function and will have an inverse. If I didn't have this restricted domain here, this would not be a one-to-one function and it would not have an inverse function. So that restriction was necessary. So g of x is just a fancy name for y, so my original function is simply y equals x subtract 2 squared. So swapping the x and y, I get x equals y subtract 2 squared, and what I need to do is solve for y. So to get rid of the exponent, I can square root both sides of the equation. That'll leave me with the square root of x equals y subtract 2. Add 2, and I have solved for y, and that is my inverse function, square root of x plus 2. Coming down here to the graph, my original function g of x is the basic function x squared shifted to the right 2, but with the restriction that x is greater than or equal to 2. So the original function g of x here is the blue line is only half of a parabola starting at x equal 2. My inverse function is a square root function shifted vertically 2 units, and that's my red line here. And notice with any function and its inverse function, they should be reflections of each other on the diagonal line y equal x, and that looks like what we're seeing here. So that's a nice way to double check your inverse function. Okay. On our graphs here, f of x equals 3 to the x and g of x equals log base 3 of x. These two functions are inverses of each other. That's how we defined a log function originally. It's the inverse of the exponential function. Graphing of this, what I did is I took 3 to the x, picked several values for x, and just calculated. If x is 2, 3 squared is 9, x is 1, y is 3, x is 0, 3 to the 0 is 1, x is negative 1, 3 to the negative 1 is 1/3. If x is negative 2, 3 to the negative 2 is 1 over 3 squared, so 1/9. And plotting those points, I get a classic exponential growth function. At negative 2, I've got 1/9. At negative 1, I have 1/3, 0, 1, and 1/3, and 2/9 gives me this blue graph here. Pretty standard exponential function. And then the easy way to do the log graphs, since they are both base 3, they're inverse functions, I can simply create a table for the logs swapping the x and y coordinates. So for every y coordinate here, I have a corresponding x coordinate. Becomes my y coordinate over here, and that gives me my red line here. Notice again, if you compare these two, they are inverses of each other's, they're reflections with the diagonal y equal x. These last two graphs are simply transformations of the two that we graphed above. The 3 to the x plus 2 would be a shift of the 3 to the x function left 2 units. So I simply took the graph above and slid it over to the left 2 units. So the point 10 came over 2 units left. The point 13 moved over 2 units left. And with that, I was able to get a pretty good graph here. Log base 3 of x plus 2, since the plus 2 is outside of the function, this one's going to be a vertical shift up 4 units. So again, I took my red line from above, shifted it up. The point 10 that was here is now at 1,4, and the point 31 that was on the previous graph is now at the point 3,5. And with those 2 points, I get a nice looking graph.